Good day, everyone. So, today my group and I are going to be talking about randomized algorithms in cryptography. So, cryptography has always been at the heart of secure communication, safeguarding everything from personal messages to national secrets. But in today's world of ever evolving technologies and attacks, we need cryptographic methods that are not only secure but also efficient and adaptable. This is where randomized algorithms come into play. These algorithms bring a unique strength to cryptography by introducing randomness, which enhances unpredictability, robustness, and efficiency in cryptographic systems. In our research, we explore how randomized algorithms can be applied to key cryptographic processes, their advantages, and the challenges they present. Today, we'll walk you through the core concepts. My name is Oswald, and I'll be taking you guys through the fundamentals of randomized algorithms. I'll be taking you guys through two major algorithms, that is the Monte Carlo algorithms and then the Las Vegas algorithms. So, Monte Carlo algorithms are a set of randomized algorithms that use randomness to produce a result that is probabilistically correct. They sacrifice certainty for efficiency, typically producing faster run times than their deterministic counterparts. In contrast to Monte Carlo algorithms, Las Vegas algorithms guarantee the correctness of the result but may have variable runtime depending on the random inputs they receive. Las Vegas algorithms are often used in cryptographic systems that require absolute correctness, such as randomized primality testing algorithms, where a failure could compromise the security of the system.
So now we come to pseudo-random generators. So first part of pseudo-random generators are key generators. So they are PRG generating secure cryptography keys for RSA or ECC. Then we come to secure encryption, used for string ciphers or block ciphers. Then thirdly, we have random number generators. So these ensure that digital signatures, ECDSA, and key exchange are unpredictable, preventing attackers from exploiting patterns. Now on to randomized preliminary testing. So for these kind of testing, we have the Miller's-Rabin testing, a probabilistic algorithm that determines whether a number is composed with high confidence. Then the second testing, we have Fermat's preliminary testing, based on Fermat's Little theorem. It's a simpler but falsely identify composite numbers as prime numbers.
Alright, so let's take a look at this diagram and analyze it. We have in the middle the application in cryptography, and we have the Monte Carlo algorithm, we have the Las Vegas algorithm, and we have the pseudo-random generators, which will converge at the application to produce the gaps in future directions. We also have the Miller-Rabin test and the Fermat primality test, which form part of the. Moving on, I'll be taking you through the comparative tables that has the algorithms, or that have the algorithms, the key features, applications of cryptography, advantages, and the trade-offs. So the first algorithm we're talking about is the Monte Carlo. Right now, Monte Carlo has key features such as probabilistic correctness. Right now, for its application in cryptography, we are saying that it includes statistical testing and key generations, and its advantages is that it's fast in execution and has low computational cost. And for its trade-off, we are saying that it's non-guaranteed accuracy and requires repetition for reliability. The next algorithm we will discuss is the Las Vegas algorithm. The Las Vegas algorithm guarantees correctness, meaning that its output is assured to be correct, and it is applicable in randomized primality testing, certificate verification. Those two, randomized primality testing and certificate verification. Its advantage is that it is absolutely correct and has no false positives. And variable runtime are based on random inputs. That's for its trade-off. Variable runtimes based on random inputs. The next we'll discuss is the pseudo-random generators, also called the PRGS. Right, so for its key features, we're saying that it is deterministic randomness, right? And it's applicable in key generations, stream ciphers, and digital signatures. Some key advantages include that it is scalable, it is efficient, and it's pseudo-random generation. Right, so then efficiency, scalability, and pseudo-random generation, those are its main advantages. Its trade-off will be vulnerability if seed is predictable. Moving on, we'll have the Miller-Rabin algorithm, the Miller-Rabin test algorithm. Right, so its key feature is that it is high confidence primality testing. It's applicable in cryptography using the RSA key generation. Some of its advantages are that it is fast and efficient for large numbers. And then for its trade-off, it's low error probability, but still probabilistic, meaning that's a low chance of error for its probability, but then it is still probabilistic. The last and final algorithm will be the Fermat primality test, or the Fermat test. Right, its key feature is simplicity, and it's applicable for its application. We're saying that rarely used due to reliability issues. Right, so then the Fermat test is really used because it has reliability issues, and its advantages: quick implementation. For its trade-off, is valuable to Fermat liars, that is false positives. Randomized algorithms in cryptography. Key uses. The first one will be the probabilistic encryption. Probabilistic encryption leverages randomness to ensure that the same plain text, when encrypted multiple times with the same key results in different ciphertext. This adds semantic security, making it infeasible for an attacker to deduce any information from the plain text from the ciphertext. That's about probabilistic encryption. There are applications such as the optical asymmetric encryption pattern, digital signatures, right? Digital signatures basically authenticates the origin and integrity of messages. Randomized algorithms are used to ensure that each signature is unique, even if the same message is signed multiple times. It has key features such as the non-repudiation, that is, the sender cannot deny generating the signature, and random per message values. Right, these are some of its key features. The next we'll be talking about the zero knowledge proofs. Right, that's the ZKP, which enables one party, that's the prover, to prove knowledge of a secret to another party, that's the verifier, without revealing the secret itself. Randomized algorithms are essential for ensuring the security and soundness of these protocols. This also has some key features like completeness. That means that a valid proof convinces the verifier, and also has soundness and zero knowledge as its key features as well. The last and final will be pseudo-random functions and permutations. Pseudo-random functions and pseudo-random permutations. Right, these are deterministic functions that produce outputs distinguishable from random given a secret key. Right, they are deterministic functions that produce outputs indistinguishable from random given a secret key. They are fundamental to cryptographic primitives and protocols. Fundamental to cryptographic primitives and protocols. Some of their applications are block ciphers, stream ciphers, and their key derivation functions. From here, we'll be talking about the challenges and future directions.
Okay, gaps in future directions or challenges in future directions. Despite significant advances in integrating randomized algorithms into cryptography, several challenges and research gaps remain. True randomness generation. Generating high-quality random numbers is critical for the security of cryptographic systems. Current systems often rely on pseudo-randomness, but weakness in random number generations have led to vulnerabilities in real-life applications. Example, the flaws in Bitcoin's ECDSA signature scheme. So future research focus on improving hardware-based true random number generations and hybrid models combining both true and pseudo-randomness. Then, post-quantum cryptography. As quantum computing progresses, traditional cryptographic systems, including those using randomness, will be vulnerable to quantum attacks. So new cryptographic algorithms such as lattice-based cryptography are being developed to be quantum resistant. Randomness remains crucial in this area, but further research is needed to optimize these systems to ensure long-term security. For last, efficient randomness in large-scale systems. In distributed environments such as cloud computing or blockchain, efficient generation and management of randomness across nodes is an ongoing challenge. Future work could explore more scalable and secure mechanisms for distributing randomness without compromising security. So by addressing these gaps, this research will contribute to the advancement of secure and efficient cryptographic systems, particularly in the areas of post-quantum cryptography, secure randomness generation, and the design of more resilient distributed cryptographic protocols.
I'm going to be speaking on the contributions and insights this report brings to light. So first of all, it addresses randomness vulnerabilities. So randomized algorithms play a crucial role in enhancing cryptographic security by addressing vulnerabilities arising from poor randomness. Predictable or biased randomness can lead to attacks such as key recovery exploit. By employing robust randomized methods, these algorithms ensure high-quality random number generation, providing unpredictable keys and secure cryptographic protocols. This strengthens encryption schemes and protects against adversarial analysis. So the second one focuses on post-quantum cryptography. In the context of post-quantum cryptography, randomized algorithms are critical for designing quantum-resistant schemes. They facilitate the construction of lattice-based, hash-based, and code-based crypto systems that rely on hard mathematical problems rather than traditional factorization or discrete logarithms. Randomization ensures the security of these schemes against both classical and quantum attacks by introducing unpredictability in key generation and signature processes. The third contribution or insight is efficient randomness in distributed systems. Distributed systems such as blockchain networks require efficient and secure randomization to ensure fairness and consensus. Randomized algorithms generate unbiased randomness that is essential for leader selection, proof of stake, and cryptographic commitments. They enable scalable and secure coordination across distributed nodes, preventing manipulation or collusion while maintaining system efficiency. So in conclusion, randomized algorithms are essential for advancing cryptography, offering solutions to complex high-dimensional problems and ensuring secure cryptographic practices. They also enable scalability, address randomness related flaws, and are vital for integrating post-quantum cryptography systems. Continued research is crucial to further enhance their development and application in securing modern systems. Thank you.